Good morning, well, good noon again. So today, inshallah, we will, inshallah, our objective of today is to finish the biasing. Very important topic. So those who missed today's class, they will have problems, for sure. Alright, I cannot guarantee the video will be uploaded this time. Huh? So again, it was just a testing experience. So today we start the biasing by asking the question where we should locate the point Q. What's point Q? It's the bias point or? But yeah, we know this intersection.
Linearity.
No. We call it, there's a name. Ali?
Operation point?
Operation point. What means operation point?
When the MOSFET operates.
Exactly. It's the point in the characteristic of the MOSFET, which is ID versus VDS, where the point where the amplifier or our transistor is working. And of course, for amplifier, it has to be in saturation. But saturation has a long path, yes or no? So one point will be where the transistor is working. Okay, correct? Good. Okay, so that's the bias point. So how we determine the bias point? So basically from the common source that we studied last time is determined in this case by the value of VGS and the load resistance. Let's go back still, okay? So remember the intersection here, I think we should also come back to this because it's the same topic here. You see, when we change the slope, how the slope, this line, what's this line? What's called this line? It's called the load line is related to RD. And RD, what is that RD? RD is the resistance of the drain. Yeah, exactly. Not the drain, but the load. Where the load is. Let's go back a little. Oh my goodness. So let's use now the mouse is much better. Okay, go ahead. Let's go. Oops. So where we are, okay, okay, good. So we said this line, okay, this line is the load line. Yes or no? That's how we define it. Remember that? Remember? Okay, let me get back again. See that no revision has been done and I'm really disappointed. So this is the load line, remember? We got it from this equation, remember? Which is the IV characteristic of the resistance. From the circuit. We did not invent it, yes or no? So that line, what we call the load line, it's written there, has a slope of -1/RD. Wow! That means if RD, we can change it, we will change the slope. If we change the slope, we can change basically the Q. Let's have a look at that. So here is the look. Let's go back, look here. See here? We are changing here the slope. If you can see here, we are changing the slope here. See? From this point to this point, see? We changed the slope. We did not change VDD, GVDD, we kept it constant. But if we change the slope by changing the resistance, we can change where Q will be, yes or no? Yes. If, say for example, VGS is set at this level, so now if I change RD, so I take it another ID, I can basically put my operating point either here, or here, or here. See? That's how we control the operating point. Got it? Good? Excellent. So, let's go. Page down. So where we were before, so boom. So that's what we are talking about, you see? Okay, good. So that's how we determine. This is number one. We are going to come back again to that issue. But in order to choose Q, because we said we know how to choose, but which one is good? Which one is good? Where Q will be chosen, okay? So let's go back. So is this Q good or this Q good? Who says that? Who determines the Q? Okay. Well, I know how to control it, but I don't know which one is good for me. So in order to answer this question, is basically Q determine what exactly? Q determine what? Determine the gain, yes or no? How? Because if you remember the gain, let's say, anybody remember the gain of the common source amplifier? Very simple, two terms.
2IS
It's not, it's very simple, the simplest one, yes? What's that? KN? V over the right. This is not the gain. Talking about gain. That's what KN V over the right is what? Remember?
Transconductance.
No, exactly, transconductance, that's exactly the point, yeah. But the gain has a two-term also formula. What is it? Yes?
VDS over VGS?
VDS over VGS. Yeah, that's how we calculate it.
Yeah.
But it's not the formula. صح, you are true. You are absolutely right. But then what's the result? That's what we're looking for. Do you understand? It's definitely correct. But you need to find the VDS and the VGS. If you find them, give me now the formula, you see? But that's the point. The formula is very simple. It is minus, remember? Minus, yes or no?
Yeah.
GM. And then, anybody else? Any clue? Minus GM what? RD.
RD.
Okay, what is Q? Q, is it in RD or is it in GM? No, it's actually in GM. Why? Because GM is equal to what, Bilal, just now?
KN.
Is equal to Kn, which is a constant, yes or no? And then? Yeah, guys, you see? The V over drive, where we get it is from Q. Is Q will determine that. Yes or no? Got it? Excellent. So that's the point. So that's number one. Number two is the swing at the output. Ooh. Swing at the output. You know what's the swing? Swing of what? All of the AC signal. What's the AC signal in this case? It's actually small v, small ds. Because it's at the drain, yes or no? Is that AC output, you see? That's a swing, it's gonna swing. You remember the previous example? Resolved it together, yes or no? So that's swing also. We need to maximize it, yes or no? Remember when we solved that problem? Remember? You didn't revise. I'm sure nobody checked it out. When we solved last time problem, we checked the swing, the symmetrical swing, you see? Because usually AC is symmetrical. It's not asymmetrical. And we said that in order to keep it, the maximum, we have to touch only the minimum voltage, which is VDS sat, which is equal to overdrive, yes or no? Remember that problem? Which I'm sure nobody has revised. It looks like absolutely true. Make sense? Excellent. So guys, please revise. The things are connected. If you miss one, you will find a problem to follow. So please do not miss. Just half an hour a day will be fine. Khalas, okay, so to have it really maximum symmetry, okay, my VDS need to be in the mid-range between VDD and my overdrive, yes or no? You understand? We'll check that later. But to solve that problem, you have to go back to that issue. Okay. Okay, what's this say? Locating again the point, the operating point, MVDC, assuming here in this case RD is fixed. Means for given RD, give me where I get Q. So the answer to this is, let's see, Q has to be between A and B, yes or no? Why? Q, the operating point has to be, because saturation, that's why. Cannot be here, cannot be there. It has to be here. Alright, so when Q is approaching B, means Q is here. What happens? Here, Q. Let's say this is Q prime, okay? This is Q given. This is one Q, we call it Q prime, okay? If we bring Q there, that means the swing is gonna be not much. This is the swing, yes or no? Because if it swings more, it will go into triangle, yes or no?
Yeah.
So that's the thing, alright? So the maximum VGS swing decreases, yes or no? As we approach, as we get closer to B, the swing has to decrease. Otherwise, we go to the triode, yes or no? Following me? Yes, Ali? Got it? Same thing for A, by the way. If we also approach A, the swing also has to decrease. So the best way is to put it in the middle. Got it? Good. Very simple, guys. It's really a joke. I mean, it's not that of a big deal here. So here, just to add here something here, you can read that again at home. Here, if we are here, so where's A in the graph? Where's that? Where's gonna be? A is here or there? If we continue the load here, let's say the load here. I think this is VDD, so this is where A is, yes or no? And here is where B is, yes or no? Yes or no? Got it?
Yeah.
Yeah, remember? It's very easy because A is close to the cutoff of the MOSFET. Good. And the B the other end. خلاص. Bingo. Now, this swing, so this is the available swing for this operating point. Huh? So it's in the small range. So we call this range the leg room. The leg room means how much I can put my leg. It's like you are driving a car, how much you have space for your leg. So this is the room for your leg. The leg of the operating point. So this is how much you can go. So it's not enough leg rooms for this guy. But if Q is close to A, so here, this guy, so you cannot go beyond this because it will, if it will do that, basically there is no current. Khalas. You know what it means? We are basically cutting the current from going through the resistor. Because VDS cannot be at VDD. That's it. Because if VDS, and I'm talking about the circuit, so you are supposed to remember the circuit, okay? So VDS cannot reach VDD. If it reach VDD, there's no current. Khalas. So this is the how much at my point can swing. So if I set it here, if it swings only here. So it's in the head. We call it the head. So it's like you are in the car, how much you can put your legs and how much you can move your head. So leg room and head room means the minimum and the maximum. Or the negative swing and the positive swing. So the head room is characterizing what? The positive swing. The leg room, no, the negative swing, sorry. Okay, how much is the minimum? The negative swing. It's not really true because the swing actually goes from negative to positive. But we are talking only about the negative side of the AC. Okay? And this head room characterizes what? The positive swing. Or the positive part of the swing. Do you understand? That's it. So ideally we need to be in the middle to have a very good swing. But the story is not over. There's another important fact that we need to consider. Because somebody will tell me it's in the middle. So fine. We go in the middle. But if you go in the middle, there's a problem here. What's the problem, sir? Let's see. All right. My goodness. Very good. Now, let's see. This is the VTC, okay? Boom, 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 boom. If we come here and we take part of this region, for example, and we blow it, zoom. What do we find? We find an important thing. And remember here, we are coming from A and then slowing down or sliding down. Yes or no? As we slide, we are not going to slide very fast at the beginning. We slide little by little. So the gain basically, which is the slope of the slide, is not going to increase very hard in the beginning. It will increase in the middle or maybe in the end. But not in the middle. We are just starting. Hey, very good. So what does it mean? It means that the gain is low. My slope is small. That's why the gain is low. That's that. Because remember, he said a very good point. The gain is what? Is VDS over VGS. Then this is the input. So the gain, which is the slope here, is really small. And to see it very small here, what's the slope of this line, of this point here? Is equal to 0. And then here starts to go a little bit down. The slope here is a little bit increasing, and then it will increase more, and then more. As I'm moving, you see, I'm moving, so it will increase. But at the beginning, it's not increasing. Good enough? Good enough. That means the gain is low. We got it? Very good. Excellent. So, so this is number one. Number two is that, here is the, remember here, we are just starting. So at the start, I don't have too much of a big linearity. The linearity is actually small. What means, the linearity is actually higher. What means linearity? So if we take this and zoom it a little, or big, so we can see that the line here, really, the nature of this line is really good, very good. It means that here I can have a very good line over a long range. Over a long range means over the input range here, this range, okay? So that's what it means. Over a good range, I have a very good line, okay? So the linearity is large, okay? That's good, that's very good. Now if we come here in the middle of the VTC transfer curve, what do we find? Excellent, so let's see. here I am in the middle of the slide. Remember this slide? It's like this. It's the same like the kid slide. I like that and still play that. Okay? I go with my kids and they play the slide. Of course, when nobody is watching, why making fun of me? So here, when I am in the middle of the slide, my speed is really good. So I'm very happy. So what does it mean? My gain is really very high. Extremely nice. That's why I choose Q to be in the middle. Beside what? Beside the swing. I can swing here larger. So the gain here is larger and the swing also is larger. So I'm very good. But there's a problem here. In the middle here of the VTC, the problem is that the linear range is small. Why? Because here is the change is really dramatic. So the slope goes zzz, and then zzz. So here the change is the linearity is very small. The range to find a good line is very small. I have to make it very narrow to have a very good line. That means the linearity is bad. That means my output will not follow my input linearly, but non-linearly, which is very bad. Very bad. Because the amplification needs to be linear. Why? The reason to have the amplification linear is because I want to have everything in accordance to everything. Means, if I have two talls, I have one has 1 centimeter, one something tall is 1 centimeter, the other is 2 centimeters. If I blow them, I need to have the same ratio between them. Means this is double of this. Now, if it's non-linear, this over this, or this over that, is not necessarily going to be 2. It could be 3, or it could be 4, because it's non-linear. There is no linear relationship. Because if I divide them, if they have the same linearship, it means the amplification will have the same factor for this guy and this guy. When I divide, the amplification go cancel each other and the ratio will be the same. Means the picture gets the same. Okay? Now it's non-linear, the ratio between them will not be the same ratio as before the amplification, which is bad. That means I distorted. Distorted means I twisted the information. I don't have accurate information of my reality, of my signal. Okay? So that's the bad thing, that's the bad news, that's the thing. So, see, very good for gain and swing, very bad too, linearity. Because in engineering, there's no perfect solution. There's something you're going to lose. And here what we are losing in this case, we are losing linearity, which is a very important thing. Okay, good. All right. If you have any questions, stop me, yeah?
Sir,
Yes.
on P, the linearity is still decreasing.
Okay, good. So, very nice. So, here, as we are approaching here the triode, means the slope eventually is going to be 0 here again. As we are approaching, of course, the gain will slow down. Will slow down. So, the gain is smaller there, similar to this point. What else? The linearity will definitely improve because I'm close to the flat. Yeah. Okay? So, not in the fall. So, the linearity will improve, the gain will decrease, will go down, and also the swing will also go down. Okay, very good point. So, basically, A and B are very equivalent. Very equivalent. All right. Good. Let's move on. All right. Let's see. Oops. Now we get to the most important time. Okay. Good. So the first biasing technique to bias a transistor. So basically, we are in the core of today's class, which is biasing. The first technique to bias a transistor is to fix VGS. If we fix VGS, we fix what? ID. And that's it. Boom. But the problem with this technique is that the transistors are not completely the same. Although they come from the same factory, but they have what we call mismatch. Mismatch means variation. We have variation because we are humans and the machines and the earth is also moving, earthquakes and the small earthquake and stuff like that. So we cannot really produce the same thing exactly every time we do it. Although we do everything we can, but never the same. One of the most important things that we fail to have exact matching is the threshold voltage. We cannot have the same threshold voltage of the same transistor, even though we fabricate in the same conditions, because all these factors. because the tools have a certainty, humans have a certainty, the earth also move, vibration, blah 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 blah. There is no what we call noise and uncertainty everywhere. So in that case, if I bring a device and another device of the same transistor, I'm not changing the transistor. I'm just taking the same type of transistors, I buy it from the same batch, but unfortunately one has a certain threshold, the other one has a different threshold. Here it's just blown up a little bit, it's too much. But usually they are very close, okay? But the problem with that is that, although they can be very close, the change in the current can be huge. Change of current, which current here? The current here, we are expressing it with VGS, not IDS. You understand? Because we are talking about what? About the saturation. What saturation happens? For this guy, it happens from here up. Yes or no? But for this guy, it happens where? Happens from here up. So even the boundaries, they are not the same in this case. So maybe for this guy I have swing, for this guy I have different swing. A little bit fine, but still. But the most important stuff is not the swing, it's actually the idea. The current here, if I have a VGS, let's say this is my VGS of my circuit. I set it with the battery, yes or no? So this is my VGS, I fix it. And that's the technique, is fixing VGS. Now, although I fix VGS, I can have two different currents. Because each device has its own threshold voltage. Do you understand? Has its own characteristics. Okay? Although it can be the same batch, but they are not going to be identical. Okay? So, fixing VGS is not a good idea because we may have variation between devices which lead to huge differences of ID. And the ID determine what? Determine GM. Remember that? GM is equal to what? 2ID over drive. Still under the effect of the March break. Still, after 1 week, guys, wake up. So the change of ID will make a big change on GM. And if GM will change, the amplifier also will follow. So we cannot have a good biasing, because my point is, can be anywhere, here, there, who knows. So, first technique out of the window, we are not going to use it. Okay, bye-bye. This is another technique. Here is by fixing VG, okay, and what? And connecting RS. We just add another condition. And why we do that? Follow me, huh? Alright. This is typically the same circuit, but the same circuit of the common source we started already. But here we just put a resistor in the source. By the way, when I ask about, this is from the quiz, when I ask about the terminal, don't give me the voltage. Because some people, some students, I asked them about the terminal, they wrote V. What's the gate? VG. Or some people, they put the gate VGS. It's not. The terminal is the gate, the terminal is the drain, the terminal is the source. It's not VGS, it's not VGS, it's not V whatever. Now, so don't make this kind of mistakes. A terminal is terminal, voltage is voltage. Okay, clear? Good? Alright, good. So let's get done. Alright, now what we have here. So basically, actually what happened is actually we've thrown RD. So RD there was thrown away, we put RS there. So this is what's happening. Oh, very good. So this is gonna be, so this is basically the curve for device 2, one of the transistors, and here for another transistor, which are very close to each other, but they have mismatch between them. And here is actually the load line. The load line of what? The load line of RS. Ooh. Okay, what's the load line of RS? Let's see. Alright, what do we have here? This is VG, and this is RS. So let me see here. How we find this? So VGS. So this line looks like this. It looks like -1 over RS, VGS. Of course, this is the total one, and plus something here. Plus something here. I don't know. Is equal to what? Is equal to ID. And this ID is of the RS. Guess what is this line? Interesting. So what's this voltage? This voltage is, what's this? This is VS, yes or no? VS, very good. And this is what? This is VG. or VG, VG only. It's not VGS anymore, see? It's called VG. You get it? Very good. Alright. So, first of all, okay, let's see. Before we get down to that, so look that ID1 is the same as ID2. That means if ID1 is the same as ID2, this current, the overdrive, actually ID1 is of the device 1 and ID2 of the device 2, which are these two, okay? So here is for the two transistors, okay? It's almost. But how do we find that? We found out this by looking at this equation in red. VG, this voltage, is equal to what? Is equal to this voltage, Vs, or VRS, yes or no, plus VGS, because this is S, yes or no, and this is G, plus this voltage, yes or no. So this voltage plus this voltage give me what? VG, which is constant, yes or no, because I fixed it. Very good. So now, we have to express VRS. VRS is equal to what? Is equal to ID RS. Very good. So ID in this case, how can I write it? ID, and I have what? I have VGS on the other side. So ID is going to be equal to VGS, VG, which is constant, minus VGS, yes or no? Minus VGS, yes or no? Divided by RS. So VG minus VGS divided by RS. And that's exactly here the slope we are talking about. Which is this slope. You got it? And so basically this is the ID characteristic of the load in another fact. And this is the constant that we were wondering, what is it? Which is VG over RS. Excellent. So, what we can get from this equation? Look at this. Here, VG is constant for both. So we can here put ID1 or we can put ID2. Yes or no? ID1 or ID2. Dependent on what? Let's see. VG is independent of the devices. Yes or no? So VG and RS, they are independent. Let's write them. Let's make them in green. So these are okay. They don't change. And what? And RS also is independent. Okay? But VGS, which one? VGS is this voltage, okay? VGS is equal to what, by the way? Let's see. VGS? No, the equation that relates VGS. VGS is equal to, yes, the overdrive plus VT. Yes or no? The threshold. Yes or no? Threshold can change, yes or no? Can change. Because threshold of first device is not necessarily the same as the other. Yes or no? So VGS can change. Depends on the device. So we have VGS1, VGS2. Make sense? Got it? Because of this guy. This guy. Yes or no? Very good. So now to minimize the effect of the variation of this one, what we do? We make this guy as big as possible. So the slope here, 1 over a big resistance, it become what? Very small, yes or no? So it's almost like flat here. So if we bring this as flat as possible, this variation will be as small as possible. Exactly. That's the key. That's the key. But of course, we have to be careful when we do things. We have to see the consequences. We may not talk about them today. Do you understand? But the trick here is to minimize, to maximize RS, to minimize the variation between ID1 and ID2. Okay? And these variations are due to the mismatch of the threshold voltage. Got it? Got it? That's the way. We lock the variation. We make the variation as minimal as possible. So that if we throw this transistor, we'll bring another one, ID is going to be almost the same. It's not going to change much. And if we fix ID, halas, bingo. We fix everything else. Good?
Yes.
Alright, good. So that's what it is. Alright. So that's what we mean by this technique. So what we mean by here, what we have here? Here is basically typically how we do it basically. We have here RD and RS. You just Here RD is really, we can put it or not, it's not really of big importance, but this is usually how we bias, using this technique, how we bias. We have two resistors, sorry, RDRS, and we have here two resistors. The purpose of this, what is the purpose of this? Is to set VG. What we call this branch? We call it what? In electronics, in electrical engineering. We want to set the voltage VG using this branch, this thing. What we call this?
The voltage divider.
Exactly. Voltage divider allow me to choose what's this voltage. We forgot that. Microelectronics and March break are killing us. Thanks Bilal. Clear? So this voltage divider will set for me the voltage VG. Bingo. So this will do that, and this will set this voltage. Once it's set, we are setting what? VG. The second one, we throw a resistance here, RS. Boom, that's it. And we come next, and we can send here an AC signal here and collect the outputs here. Okay? The other technique here is basically what? But here is a little bit advanced. It's not really advanced. Here we set the voltage here as what? Zero. That's it. Boom. But here to work, we have to make this one negative. We have to. Otherwise, it doesn't go anywhere. Yes or no? So boom, this is another technique. So either using this or this to bias with this technique. Okay, good. Now there's a problem here. We can solve it if we have time. Let's see it later, okay? Alright, this is the problem. I'm not gonna talk about it if I don't have time. So if we have a circuit like that, what we discussed last time, the rule of thumb means the design rule of thumb. That's how we usually do it for many reasons. I'm not going to discuss that. Is that when we put this resistance RD and RS, we try to divide here the voltage. So here and here, the voltage between this and this is the same from here to up, is the same as here to there. So we basically divide the whole voltage range here into this, equal to this, equal to this. So this voltage drop is going to be third of the whole thing, same here, same here. Okay? So here is the third of VDD, and here is also the third of VDD, and here also we put it as a third of VDD. VDD basically is the range from the power supply to the ground. You understand? This is the rule of thumb of the design. That's how we design it usually. Okay, if we have time, we will discuss that. Now the question is, we need to choose RD and RS based on this assumption. You can enjoy this at home. Okay? So basically the designer will come and say, hey, listen, I need a current of this amount and design for me, and I need VG at this voltage, design for me the circuit. So the role is now to get RS and RD. Okay? So it's straightforward. If you have problems, it's let me know, okay? And it's also solved in the textbook. Alright, another technique here. So we have first one, fixing VG, second one, fixing VG and adding RS. Now, the third one, what we do, we add what we call a feedback resistance, here RG. The role of RG is not visible as of the biasing, but it will happen later on, okay? So here, we try to find basically again the bias point. Let's see. Of course, there's no current in here. Because there's no current in here. Make sense? Good? Yes or no? There's no current going through, so there is no current going there. So this means that this voltage is the same as this. So here means VD is the same as what? V? No. VG only. That's it. I have to look at S first. But S is ground, so they are both the same. So I can add here S without problem. So this is how we should think. Do you understand, guys? And the source is actually one of the questions, also one of the answers. Somebody put, for example, for the terminal drain, put it here. No, the drain is here. Do you understand? And the source is here. Do you understand? The terminal is not away, it's here. Some people, they throw it away. Huh? We don't do that. When I find a mistake or comment, I will let you know. So we did that. So VDS is equal to VGS. Hey, is equal to what? Is equal to VDD minus RD times ID. Yes or no? That's what we know. Make sense? Good. Hey, very good, very good. Now, the nice thing about it, ID can change due to the mismatch. Yes or no? But VDD is constant. Green. RD also is constant. Green. Oh, very nice. So I'll bring this constant. Huh? And also this one VGS change or no? Change, because this is the source of the change. VT is in VGS. Remember that? VT is in VGS, and that's why it makes ID not constant. It may change from device to device. So what do? We bring these guys on one side. So this is changing, this is which one? This is changing, and this is what? Constant.
Yes.
Okay, and this is also constant. Very good, excellent. So what does it mean? It's the same story like we did last time. So ID, I can write it. We come from here. You can write ID. I will choose the red one. ID is gonna be equal to what? VDD over RD. Yes or no? VDD over RD minus VGS over what? Over RD. Hey, very good, very good. So which one is changing? What's changing is in the red is this guy. But I can make this minimal by maximizing this. By making this high as possible. So if I make it high, this can change the mass or not. This over this bye. So the only thing that will set ID is what? Is the constants. The green ones. VDD, I forgot this. Sorry about that. VDD. So it's set now ID is mainly due to this. The green. Green, guys. This green over this green. Green over green. This I'll maybe make it go down. Make sense? Same equation that we found last time. Remember? Let's see.
Professor, but practically it cannot go to 0, right?
Oh, of course, no. Yeah, if it goes to 0, bye-bye. But we minimize only. The same equation that we found here, remember?
Yes.
The same. This is green over green. So this is ID set now by the green parameters, not the red one, which is this one. See? It's mathematics in electronics. Enjoy the beauty of math. Alright. So this is good. So let's see. Almost there, guys. Let's keep up the good work. We come to the promise to talk about the different amplifiers using MOSFET. So these are the different amplifiers. We talked about them. So as you can see, in these amplifiers, we don't have VDD and VSS. They are not there. Why? We'll talk about that next. So this is the one that we studied just now, which is the common source. Why? Because the source is connected with common. And this amplifier is actually common what? Common gate. Common gate. Yes or no? CG. And this guy is common what? Common this guy.
Drain.
What's this?
Common
drain. CT. Very good. These are in the AC domain. You have to write that very clearly. Okay? AC domain. Why? Because the following. When we go from DC to AC, of course we have to do DC analysis, then move to the AC analysis. Any constant voltage, from DC will become what? Will become a ground. In where? In AC.
Yes.
Ground or short circuit. I will write it completely. Or short circuit. No, I can have here, see here, what I had before, I had this guy connected to VDD. Yes or no? Now VDD, there's no connection after VDD. Or you can take it, is actually between VDD and the ground. Now I don't have, it's short circuit, so VDD terminal will become what? To the ground. Bingo, that's it. And this is, here, suppose for example in DC I have here constant voltage for example. That constant voltage becomes what? Short circuit. That's nice. And things like that. Here we have the DC power, DC voltage, and an AC voltage. Now we have only the AC. Why? Because the DC becomes what? Short circuit. So any constant voltage becomes 0. Or short circuit. Same story. So this is one. This is applicable to all amplifier configurations. You understand? So that's what I mean here in the bold one. What we mean by common is actually we mean the terminal, in this case, for this one, for example, here, we mean the source, the source in this case, is common in the AC domain. Do you understand? it's not in the DC domain. That when we say common source, we are saying common source in the AC domain, not in the DC domain. We started in DC, but now we know the reality. This is what we mean. Okay? Any question about that? So that's what we mean. These are the different configurations. We'll try to study all of them. If we have time, of course. Yeah, I need time. How we characterize an amplifier? An amplifier is an electronic device. It has characteristics. When you design it, you give it to customer, you tell him this is good amplifier. He tell you, how do we know? Yeah, then we try to sell our amplifier. We mean business. Yes, we are selling this. Amplifiers, you find them everywhere. You find them in the headset, you find them inside sensors. The sensors are everywhere. You find them everywhere. These are the typical characteristics. We have the first one is the input resistance. The input resistance is what? Is the input voltage divided by the input current.
Yes.
We send the current and we measure the voltage. We divide by 2 and then boom, we have the array. The second characteristic is the open circuit voltage gain. Means I have the amplifier but I have no load to it. At the output there is no load. Okay. No load, that means big resistance at the output. Or it's open. Same thing. And here we are talking about the voltage gain, open circuit voltage gain. That means output voltage divided by the input voltage.
Yes.
Without any load, or with a load that it has a resistance unbelievably big. The third one is the voltage gain. Here means what? It's not open circuit. That means we have a load. Yes or no? So it is equal to this gain multiplied by this ratio. We'll talk about that one next. Or shall we do it now? Okay, do it now. So let's see. What we see here. So here we are in this case.
Yes.
We have a load resistance and things like that. Very good. So, so what we have here. So the output voltage here is across Rn. Yes or no? Yes or no?
Yeah.
And the current here of the transistor is equal to AV naught times V input. Yes or no?
Yes.
The input voltage times the AV naught without having any load. Yes or no? Will give me basically the current that is going out. Yes or no?
Yes.
That's what it is. Or actually it's not the current. It's actually here is equal to V output without resistance. Rn is equal to infinity. Yes or no?
Yes.
Yes or no? Very good. So here if I draw it again, so it's like this. So I have here this resistance R out. We'll talk about it. We have already. Well, before with this, we should have spoken about this. So let's forget about this for now, because we need to describe what's R naught. R naught is called the output resistance, which is basically we send here at the output, we send the current in, okay, and then we measure the output voltage, and then we divide them. But we have to make a condition here is that we don't have any input voltage. So the input voltage here is grounded. And then we do that. Why we do that? Because if we make Vin here equal to 0, that means this guy will become what? 0. And the only resistance I can see from here is only this. And here is grounded. So it's only this one. So this one we call it R out. Or the output resistance. Do you understand? So we have to ground the input voltage in order to calculate the output resistance. Good? Good enough? Now we come back to the voltage gain, this one. So we mentioned that to find the voltage gain we have to have this. So very good. So here we have to calculate the output voltage. So we have here R naught, yes or no, which is this one. And then from here to the ground we have this resistance, R load, yes or no? We know this voltage is how much, this voltage is what? Is actually from the ground to this point, which is what? Which is this voltage.
Yeah.
It's AV not V input, yes or no? And the output voltage is where? It's cross RL, yes or no? Yes or no? This is what? The common ground everywhere here.
Yes.
Ah, very good. This is what? This is what? As Bilal mentioned. Voltage divider, yes or no? So V out is equal to what? Is equal to all this times what? So let's write it. So V out is going to be the whole voltage range, which is AV, V input. صح ولا لا?
Yes.
Or AV, V input. Yes, it's not V out. It's V input here. Okay. V input. That's the whole range, which is this voltage, Which is this voltage, Okay. Times what? Times RL divided by RL. Yes or no? Yes or no, guys? Are you following me or not? Following or not?
Yes.
Times this resistance divided by this plus this. This is voltage divider. We know that,
Yes.
315. Prerequisite.
Yes.
You don't know it?
We
Go
know
back.
it.
You have to know it. صح, very good. So is that the result or no?
Yes.
Yes. Then we bring this down here and then boom. Look at this. What is that? This. Yes or no?
Yes.
Got it? Clear. Alright, good. This formula will help us in here. So here is the same thing. This voltage expressed with this voltage is going to be also voltage divider. This voltage is going to be the whole voltage from here to there times this divided by this plus this. Yes or no? Times R in. What is R? No, we're talking about this one. Here. See here? The voltage, input voltage, with respect to the input signal. Because here, this is the voltage generator. Yes or no? Any voltage generator has a resistance. Yes or no? And we call it R signal. And the voltage supplied by the voltage supply has also voltage. We call it V signal. Yes or no? So the voltage at the input of the amplifier, right at the amplifier, is equal to the whole voltage in here times this divided by this plus this. صح ولا لا? Which is this formula. Is a voltage divider there too? صح ولا لا? Did you get that or no? صح. How? Okay, we repeat. The voltage from here to there is actually V signal. Yes or no? I will choose a different. I will. This whole voltage is actually V signal. Yes or no? Yeah, it's this one. This voltage, same like this one. صح ولا لا? And this voltage here is V input. You see? صح ولا لا? So what's this? The whole thing here is voltage divider. Yes or no? So this voltage is going to be this voltage times this divided by this resistance plus this resistance. صح ولا لا? Got it? Clear, Faraj? Sarajdin? Good? Clear? That's it. So now we have what we call the overall voltage gain. What's the voltage gain, overall voltage gain? It's going to give me the voltage from the output all the way to the input. It's actually V out with RL divided by the V signal. So it's going to give me what? This is what? This is actually V input over V signal. So let's do that. So this, I will write it on top so that it's clear. So this is this. So is this V input divided by V signal. And AV naught is actually V out divided by what's this? Is this whole thing? Yes or no? Is actually V output over V in. Yes or no? So this cancels with what? With this. Will give you what? V out, of course, with RL divided by V signal. Do you understand? V output divided by V signal. And that's actually the definition of the overall gain. V output divided by V signal. Do you understand? So the formula is actually the gain from all the way from the output to the input. Actually from the input to the output. Do you understand? Got it? These are the characteristics of your amplifier. So you have to do this for every single amplifier. Lots of questions. We'll have fun in the quizzes and the fun. Yes or no? Excellent. So let's keep going. We don't have much time now. We'll start with the first amplifier. We'll stop here, inshallah. We'll have to do it very quickly. Here is very simple, actually. What's the input current? This is the input. Yes or no? This is the output. Yes or no? So the input current is equal to what? Yes or no?
Yes.
Here the input current, how much? Bilal, what's the input current? You're looking at the, no, come on. Yes, current is equal to 0. Come on, guys. There's no current going from the gate.
Yes.
What's up? You said 0? Yeah, you raise your voice. I'm not sure. That works against you in this case. The current is equal to 0, so the input resistance is equal to infinity.
Infinity.
صح ولا لا؟
So.
There's no current. V input over I input is equal to 0. No calculation. Did you calculate anything?
No.
Bingo. خلاص. Very good. So AV not. So we don't have any load. We don't have any load. But before we do this, this is in DC. Basically, this is the amplifier as we know it. We have to convert it to AC first. Okay. So what's that?
First one, is it in both?
No, here is the first amplifier without DC and AC. DC and AC. So we have to go to AC domain. In DC, we already found the quiescent point and boom. And we have to come to the DC. So we bring VDD to the ground, yes or no?
Yes.
And we have to take this out. So
To the ground.
we have only this. There, you see? And that's it, we have this. Now, we have to replace now this. Now remember what we did last time? This is the model. The AC model of the MOSFET. We have R0, we have GMVGS, blah blah. Remember that? You see, now kicking, very good. And now we have to replace this with the model that we have. See now things, now the puzzle is getting complete. Now we have, this is the circuit. Very good. So we need to have a V out. What is the load? The load is supposed to be here at the drain, yes or no? But we didn't put any load here. We have only RD. That's good. Very good. So AV naught is going to be equal to V out over V input, yes or no?
Yes.
Without any load. We didn't put any load. Now, to calculate that is very simple. The whole current here, we know it, is GMVGS, yes or no?
Yes.
It's going to be times this in parallel. That's it. So this is the current times the total resistance. Are they parallel with R0, yes or no? And then divided by the input. The input is what? The input voltage is nothing but VGS. So now VGS with VGS bye-bye and bingo. Yes or no?
Yes.
That's it. We have the gain. Very good. Now the next one is R out. R out is dx over Ix. Means if I send here an input current here, how much is going to be the voltage? And that is very simple. When we ground this, VGS is going to be equal to 0. The current will be what? 0. So this is 0. That means this is open.
Yeah.
Very good. So when we send here a current, we find what? We find this resistance in parallel with this.
Yes.
And that's what it is here. And because R0 is very big, when we have two resistances in parallel, the smallest will be the one. Yes or no? So the smallest is what? Typically it's RD. Why? Because R0 is extremely high. Remember that?
RD. Yeah.
We talked about it. Yes or no? Again, revision. And again, if you don't listen to me, you will have problems. Good luck for you. That's it. We finished with that. Now, the inputs here. Okay. Now, is there any current here? There's no current.
There's no current.
That means this is going to be the same.
Yes.
That's why we put this. Or you can apply the same formula that we have before. Good. Very good. And now, the overall voltage gain. Now, if we have an RL here, it's going to be here. Yes or no?
Yes.
It's going to be here. Yes or no?
Yes.
So, that's it. So, that's what it is. The output now, because this becomes in the ground, and this is in the ground. So, these two are in the ground. So, they become what? Parallel. That's it. So, here, then in this case, I have GMVI, which is this current, times all this in parallel. Divided by this voltage, which is same as this one.
Yes.
Then this will go with this, and bingo, we finished the last characteristic. Now, something to take home today. So we talked about this already, so this is an extra thing for you, so it's not big deal. It's the same thing. What's this? Yeah, we finished by today class this. Very good. Now, assume that we put now RS in here. Find everything. And if you get everything, you will get the bonus. Cheating is not allowed. Why? Why the cheating is not allowed, guys? We need explanation here. Yes or no?
When do you require this to be finished? By homework, next class.
Okay. Thank you very much.
Is it the small signal voltage?
No, R signal is the resistance of the signal generator.
But in the initially we don't have any R signal, the DC and AC.
R signal is actually of the AC signal. Where we get this from? Do you understand?
Is it from the small signal model?
Exactly. No. R signal comes from the input. You see, when you generate your AC signal, you generate it from somewhere. Yes or no?
Yeah.
That somewhere has a resistance. That's all.
Oh, okay.
Do you understand? It comes with the source.
Yeah.
So the source has the voltage swing and the resistance. Yeah, that's what it is. All right. Thank you very much, and see you next class, inshallah. Okay. Thank you.